Hey everybody, this is Larry. This is March 10th, though I don't know. I mean, the days don't matter. I'm gonna do an extra bonus problem, so definitely, if you feel like you want to do an extra problem because today's daily problem is easy, then yeah, you're in the right place. Let's get an RNG problem, and we do have a premium problem, unfortunately, but it is 2436. Minimum split into subarrays with GCD greater than 1. You're given an array numbers consisting of positive integers. Split the array into one or more disjoint subarrays such that each element of the array belongs to exactly one subarray and the GCD of each subarray is strictly greater than 1. Is that the minimum number of subarrays that could be obtained after the split? Okay. N is 2000. My first thought is either that it could be... It's either DP or greedy. I think the thing about GCD is that the more numbers that you have, the lower the GCD is, right? It's just the way that it's set up, right? It can because GCD is how do you say it? It's distributive, commutative, and all these things, right? So like yeah. So it'll get smaller as you go. So definitely, in a greedy way, maybe that would work. But yeah, I'm trying to think where the greedy works, but I think the DP is actually pretty straightforward as well, to be honest. It's just having a suffix and then you have the longest path in the DAG, right? Wait, minimum split? Then shortest path, sorry. Shortest path in the DAG, right? Basically, the idea about constructing the graph is just, from the first index to the last index, kind of. I mean, I'm kind of hand wavy a little bit because that part is this problem doesn't seem that interesting as a result. I don't know if it's gonna be fast enough, but let's wait it out, right? So you have dp is equal to say infinity times n, right? You have n is your length of nums. Let's just make this n plus 1 actually, I think, right? And infinity is just big number, and then yeah, dp sub 0 is equal to 0, right? And then now, yeah, for j in range of I, I think I have to do it the other way. Yeah, for j in range from I minus 1, right? Something like that, right? Well, basically, we're saying that, okay, now for the ith index, we want to just look at all the previous one. So this is going to be n squared. Hopefully it is fast enough, because n squared, 2000 square on Leetcode is not always guaranteed, because Leetcode just don't really think about it too much. But we'll see. But yeah, basically GCD. Okay. Yeah, g is equal to num sub I, and then yeah. Well, I guess technically we should start at I. So then now g is equal to GCD of g and num sub I, right? So, and then if g is equal to 1, we break. Otherwise, then g is greater than 1. So then we can take this. So then we now say dp sub I is equal to min of dp sub I, or dp sub j minus 1 plus 1, right? As a way to kind of calculate that, and then we just return dp sub n after that. It should be okay, maybe. Maybe silly mistakes. I guess it's always possible, so why is it... Well, wait. Did I mess this up somewhere? Probably. Because this doesn't go to n, because it's not dp sub I, it's dp sub I plus 1 to get the one to the left. And then j is going to be the jth element, so actually, yeah, off by 1. Oops. Because I started at 0 so that we can, yeah. And the reason that we have it at 0 is okay. Well, let's take a look first. But the reason why we have a 0, just for a little bit illustration, is because we don't actually care about the index. Or we care about the index, but what I mean is that we want to the nodes on this graph is actually the space between the things. So then now, and you want to get from this first node to the last node in the shortest path, and of course you just have to go through it. Yeah. I mean, also, I want to say that this is n squared, obviously, in the worst case, but like, for example, in this one is going to be n squared, but because of this, it actually runs faster than that on average. But yeah, all right, what are we doing? Right. Expected 2. Why is that? Let's print it out and find out. 1 1 1 1 1 2 2 2. Why? Okay. I guess I should have expected that actually. But okay. So then print GDP sub I. IJG. Maybe that's fine. I don't need the other one. But all right. So we have 12 6 6 3. Oh, and then it terminates. Okay. That's good. Were we at 4 0 1 2 3? Did I do something weird? Where's the 8? Where's the 4? Am I off by 1 somewhere? At the very least, it should show up once for oh, this is I, that's why. Okay, I'm just being dumb. Okay. Okay, I mean, there's still some stuff to investigate, but oh, there we go. There's the 4. Oh, because actually, it's unclear why that didn't show up in the debug. But anyway, that's a bad typo. Oh, it doesn't show up in the debug because it does the 4 and then it does, like, I don't know. All right, let's give it a submit, and yeah, that's pretty much it. Man, I cannot solve a problem without a silly mistake. I don't know what to say. But yeah, that's a bad typo. But yeah, basically we take advantage of the distributive property. We know that I think I didn't go with that part. Like, that's why we go to scan. But let's say we have this number, right? And we're just saying, okay, let's say we're at 14. Then now, let's just say we want to say 6. I'm going to use G as the GCD operator. Because like you have something like this to find the GCD of these 3 numbers, then you could actually just do it this way first, distributive property. You do it this one, you get the number, and then you can't do it that way. So that's basically what I'm doing, like a progressively, like a progressive GCD. And yeah, and we just have to make sure that this is not equal to 1, because once this becomes 1, then it just cannot go any further, right? And then if it's not 1, then we try to see if we can, we connect that to get the shortest path in the DAG. Yeah, this is going to be n squared time, O of n space. And yeah, that's all I have with this one. Let me know what you think. Actually, let me check something real quick. I wonder if there's a greedy solution. I'm curious. There is a greedy solution, huh? Okay. I think that's the thing, is that I was thinking about this. I mean, greedy is quote unquote obvious, but I wasn't sure that like, the proof is harder than the code, right? Like, the code is pretty straightforward, but the proof is way harder. That's why I wasn't sure. I don't know. Don't know what to make of that, to be honest. How would I prove that? I guess the GCD is a weird thing about it, at least for me, that I don't know. I guess the more that you put it in the initial thing, I guess you could do an exchange argument type thing of like, okay, let's say you have a middle element between 2 subarrays, and you can merge with either the left end or the right. If you can merge to the left and it's still and by that I mean that like the GCD is less than 1. If you merge to the left instead of the right, then you have more, like in a greedy way, the one to the right has more possibilities to stay above 1 kind of thing. Is it a great explanation? I don't know, to be honest. I think that's kind of the structure for the proof, though, to be honest. But it still feels a little bit, I don't know, just for me, not practiced. Like I don't practice GCD properties enough to kind of be confident about it, right? Like it makes sense. It follows. Am I confident about it? I would not be confident on a contest. Here, I don't have to prove anything, which is why this is how I did it. That's all I have for this one. Let me know what you think. And yeah, stay good, stay healthy, do good mental health. I'll see y'all later and take care. Bye bye.